Our team of structural engineers and experts have joined ARC project from the beginning. This was 2.5 years ago, and we developed the concept for the structure, and then we went on with developing the building permit documentation and technical project, and we are now in the phase of supervising the execution works to completion and to make sure that the detailed design is being implemented as designed. The building structure was designed having 3 main concrete cores with very thick shear walls, 70 or 60 centimeters. And then the slabs are flat slabs. They are actually, let's say, hybrid slabs with thicker stripes along the column axis with perimeter beams, and this is basically the entire system. So the concrete cores are providing structural strength and stiffness, also for horizontal loads, for earthquake action. Going on with the structure, I must say that it has a very stiff and strong basement system with very strong concrete walls in both directions, and with a thick mat foundation of 1.6 meters. It has a very high concrete class in the structural elements, up to concrete class C50-60 or C40-50. The building altogether has more than 29,000 cubic meters of concrete, more than 5,000 tons of steel. The total weight of the building is more than 6,000 tons. This is, if you want, like a cargo ship on 150 meters long. This is mainly due to the very thorough seismic design and structural strength required in this region of Romania. The structure of the building, it's actually made of 3 concrete cores. They are made of shear walls, 70 centimeters thick or 60 centimeters thick, reduced to 50 centimeters and top 2 stories, and flat slab, which is actually a hybrid slab. It doesn't have the same thickness all over. It has thicker stripes along the columns and thinner areas in the center of each span with perimeter beams. And actually this flat slab system allowed us to comply with the client's requirement of having a quite big clear story height. This was a specific requirement. The client wanted to have 3 meters clear height, and we could achieve this considering that the building story height is 3.9 meters from top of the slab to top of the slab. Then if we consider also ceiling below the slab with all the ducts and everything going on, we could accommodate all this, keeping the 3 meter story height. And this is quite an achievement in terms of, let's say, functionality and space and quality of the space that the people are going to work in. This, let's say, rounded corners, if you want. I'm not an architect, I'm an engineer, but I believe they will have a very big impact, because I haven't seen this in any of the office buildings in Bucharest, at least. And I believe the overall design and aspect of the building is quite unique and very beautiful. I honestly think that for the people working inside will be a very nice experience. Some of these corners were very challenging, the convex ones, because we had to make sure that slab is stiff and strong enough between the columns, and which have a very big span in between. Of course, we analyzed several possibilities, and the optimal one was chosen in terms of strength and costs. So a balance is always there between strength, safety, stiffness, but also reduced costs. The position of the pillars is dictated by the grid of the structure of the building, and the grid of the building is established by the architect, who is, let's say, the overall boss of the entire design, of the design phase. So we as engineers, we have to comply with this, and we have to design accordingly. The structure is very safe, but I have to say, because I've been doing this profession for 22 years now, it is as safe as any other structure designed by respectable company and with good engineers. It complies, of course, with all the norms and all the design codes. If I had to throw a few numbers, it is designed to sustain a seismic force or seismic ground acceleration, actually, up to 0.36 G. This is 60% more than the highest ground acceleration ever recorded in Bucharest. During the earthquake in 1977, the ground acceleration was the highest ever recorded here. It was 0.2 G, almost 0.197. And this building is designed for 0.36 G, horizontal seismic force. So this kind of design doesn't mean that the earthquake will be higher, but it means that the building will have virtually no damages in case of an earthquake. So no cracks, and it will be fully functional. The hybrid flat slab, as any flat slab system, compared to, let's say, a classical system with beams, which lead to a thinner slab, it only has one, let's say, small disadvantage. It costs a little bit more than a classical system with beams. In terms of safety, it is as safe as any structural system which is correctly designed and built. So you have to make sure that the concrete cores are stronger in case of the flat slab. Everything is very safe. It costs a little bit more, but it has the big advantage of creating a bigger story height. This foundation system of the building as a whole, it was chosen to be a flat mat foundation and not a piled foundation, because it was not necessary for this building. The soil is strong enough and the foundation is strong, to some extent flexible, and is able to, if you can imagine a mat on sea or on water, it is able to accommodate forces and deformations, which is why it was the optimal solution for this building.